Most physicalizations are static data representations, but we as a community know that interactions are critical for working with data. So naturally we ask, how can we create interactive physicalizations? But creating interactive physicalizations is difficult because it requires cross-disciplinary knowledge in various domains, including visualization, fabrication, and electronics. And because of this challenge, I argue physicalization as a field lacks generalizable approaches, particularly for its interactions. When interactive physicalizations are produced, they typically stem from an unstructured manner, which results in unique solutions, whether it's specifically for a dataset or a particular form. And I believe this lack of generalizability is one of the biggest barriers to physicalization adoption, as most physicalizations cannot be easily extended or adapted to new scenarios. And so to support generalizability, our research contribution is a computational design pipeline that concurrently considers form and interactions, which can enable developers to 3D print various network physicalizations that have sensing capabilities. By leveraging multi-material printing and computational algorithms, our sensing networks support node selection. And so when a user touches a node, different applications can recognize the node selection, including desktop, and even AR and VR. Now I would like to discuss the motivation as to why we focus on networks. So when constructing this computational design pipeline, we focus on networks for two primary reasons. First, networks as a dataset are ubiquitous. Almost every domain uses networks in some shape or form, which aligns with our objective of promoting generalizable approaches. Second, from an engineering perspective, networks, even as something as small as this one, have complex geometry and will require significant engineering considerations to make them physically interactive. The traditional and popular approach is to use off-the-shelf electronics. And here is one of my earlier prototypes where I was trying to support node selection, but you can see the complexity of the wiring for even supporting 2 nodes. Imagine trying to follow this approach for 50 nodes. And so, more recently, researchers have also begun to use computer vision. But computer vision introduces other sets of challenges like occlusion and inaccurate alignment. So that is why, in contrast to these 2 approaches, we aim to leverage the 3D printing process to directly print electronics so that we can fabricate fully interactive products that can be ready to be used straight off the printer. And the objects that you see on the screen, including our network, can detect interactions through capacitive sensing, which is due to the use of the conductive filament, which are the black materials that you see in these prints. And capacitive sensing, for those who may not be familiar with the term, is a very common technique, and that one that you probably encounter on a daily basis. It's a common technique to capture touch input on devices like smartphones and tablets. So now I would like to talk about our computational pipeline itself. And I would like to note that one of the strengths of our pipeline is its automated process. The only actions required from the user is to simply upload a network dataset and then wire the 3D print to a microcontroller. All of the other steps is handled by our pipeline, including how to enable capacitive sensing. And so now I'll explain how we achieved capacitive sensing, which largely focuses on the first half of our pipeline. So after a user uploads a network dataset, the objective of the first half of the pipeline is to automatically generate conductive traces with tuned electrical resistance so that they can be integrated into the links of the network physicalization. These conductive traces, which are these black serpentine patterns that you see in the bottom half of the figure, are computationally designed to exploit a phenomena called RC delay. And now I'll illustrate what RC delay is with a simple network. So RC delay is the time required to charge a capacitor in a circuit through a particular amount of resistance. The capacitors in this case are the nodes. Increasing the resistance in the circuit will also increase the amount of time needed to charge the capacitor. So for example, when touching node A would require 7 microseconds, as opposed to node B would require 14 microseconds. And our pipeline is based on this principle. We can design networks where RC delay varies based on which node is touched. Here is an example of RC delay in practice. This is a network of 4 nodes and 6 links, and you can see that we can obtain unique RC delay values for each node because of the tuned conductive traces. So to support capacitive sensing, we have established that we need to embed a circuit inside the network. And this requires determining 2 things. First, which links should be the resistors, and second, what should their resistance be? The combination of these 2 factors influence the RC delay phenomena. But figuring out these 2 parameters manually is too troublesome. There can be several ways to embed a circuit within a network. Here is another example of a network with 7 nodes, but you can see that there's already 2 options of how to embed a circuit. So to automate this process, our pipeline uses circuit simulators and a gradient-based optimization to find the optimal resistance so that we can clearly recognize the different touch points by exploiting different electronic principles. But for more information, please check out the paper. In parallel, our pipeline also needs to consider how to lay out the network in 3D. We use a neural network to accomplish this for 2 reasons. First, it can help us avoid overlapping of nodes and links to avoid circuit interference. Second, the neural network can be used to create different loss functions to optimize for different graph aesthetic heuristics like uniform length. Now, I'll be discussing the second half of our pipeline, which focuses on fabricating the output results from the first half. So now this includes generating a digital representation of the geometries that we want to print by using a CAD software, including the conductive traces. As you can see here, we use a serpentine pattern to control the length of the conductive traces so that we can vary the resistance within each link. Then we use the output of the CAD files to prepare for 3D printing. After 3D printing, the last step is to wire it to a microcontroller, which requires at most 2 wires. Now, we have a sensing network physicalizations that can serially communicate with other devices. We evaluated our pipeline using 3 approaches. Today, I want to discuss mainly the 3rd evaluation. For more details of the other evaluations, please check out the paper. But as a quick run-through of the 2nd evaluation, I want to note that our algorithms are not the bottleneck of this process, but rather the physical fabrication process itself. Our algorithms can find optimal results for large network datasets like 50 nodes and 500 edges, but we're currently limited to the physical print bed size, which constrains us to, at realistically, 20 to 30 nodes. Using this fabrication limit, we fabricated the largest network that we possibly could using our particular 3D printer, which resulted in 20 nodes and 40 links. We used this network to explore 3 usage scenarios stemming from general visualizations tasks, exploration, explanation, and provenance. Because the network can serially communicate with other devices, the network can complement other visualizations for interactive exploration. At the same time, we can collect data about the user through the different touches that they impose on the physicalization, which can be used for meta-analysis about the user's sense-making process. We can also use the sensing network physicalization to explain our findings. This can be very helpful in contexts such as science museums or remote presentations. Now, I would like to move on to the discussion part of this talk. So when we revisit our motivation, I explained that designing interactive physicalizations is difficult, but the results of our work indicate, benefits of further investigating and developing other computational fabrication processes for physicalizations. And when we take a step back, I see parallelism between our work and current visualization authoring tools like D3 and even ParaView and VTK. Digital toolkits have reduced the time and labor to develop visualizations. Before these libraries and softwares existed, developers had to use general graphics applications and had to develop their own custom solutions for common operations. Toolkits for physicalizations have the potential to achieve similar goals, enabling developers to focus more on what analytical scenarios they want to explore with a physicalization rather than how to build one. And from that, I want to note there are several interesting opportunities to continue this line of work. And I particularly see 2 threads of future work. Regarding our method itself, there needs to be more work done to improve different aspects of the pipeline, such as improving scalability. But there's also a new line of work where others can use our approach for other visualizations beyond networks. Visualizations and other freeform interfaces can be deconstructed into network-like shapes, like low-poly 3D models or even points within a line graph. So we believe that our approach is generalizable for even other visualizations. And so in summary, to support generalizable interactions for physicalizations, our research contribution is a computational design pipeline that concurrently considers form and interactions, which can enable developers to 3D print various network physicalizations that have sensing capabilities. And with that, I would like to thank all of my co-authors on this paper, and please feel free to reach out with any questions you may have and check out our project page. Thank you.